So going back to the examples that we took, if we run those same examples in this situation, what do we get? 1, 2 minus 2, 3. The set, the elements in the first set which are not in the second set. 1 is in the first set, it is not in the second set. 1. 2 is in the first set but is also in the second set. So 2 will not appear here. And that's it. Because we are considering only sets, only elements in the first set. So this is the difference. Now note that unlike union and intersection, if we calculate this one, we get 3. So difference of two sets is not commutative. Okay, A minus B is not B minus A. Of course, it will be equal in a special case when they are both the same set. Okay, so this is the first example. What about this one? 1, 2 minus 1, 2, 3. Those elements in the first set that are not in the second set. Is there any element in the first set that is not in the second set? No, because both the elements in the first set are also in the second set. So that means this difference has no element. It is empty. However, if you calculate this one, those elements in the first set that are not in the second set, only one such element, 3. Similarly, since we have been taking that complicated example, we include it here also, just for the sake of it. This minus empty set 1, 1, 2. Those elements in the first set which is not in the second set, these are already common elements, so they will not appear in the difference. 1 is there in the first set but not in the second set, so this is the difference. Similarly, if you take this minus this, that set would be the singleton set consisting of the empty set. Okay, so this is difference. Now, just like union and intersection, difference also has some properties. In fact, many properties, although one or a set of properties is more important than the rest. But before going to the properties, just like intersection had a special case where we had disjoint sets, difference also has a special case. See, when B is a subset of A, the difference A minus B is called the complement of B in A. It may happen that whenever you are taking difference, for example, in this case, here this is our A, this is B. So if we draw Venn diagram, this is my A, 1, 2, 3, and this is B. The one sitting inside of A is B. So in this case, if I calculate the difference A minus B, what do I get? 3. So this difference in this special case where the set that I am subtracting is a subset of the first set is called the complement of the set being subtracted in the first set. That is, whatever is not in the subset. This is the subset. Whatever is not in the subset, this is the complement of the subset. And in this case, you clearly see it's 3. Okay, so this is just a terminology that is used. You cannot use the word complement in a situation like this. If this is A, this is B, you cannot say that this is the complement of B in A. No, because here B is not a subset of A. Only when B is a subset of A, we can use this phrase, complement of B in A. That means whatever A has that is not in B. B and its complement make up A. Together taken, they make up A. And even there is even a more special situation where if A is equal to U, a universal set. Okay, if A is a universal set, I have already talked about universal set in a previous video. It is a set which will contain all the elements that we are going to discuss, and it will contain all the sets in our discussion as its subsets. It must be that large. It must be large enough to contain all elements as elements and all sets as subsets. So if A is U in this special case, then automatically B will be a subset of U, because then only it is universal set, because the set I am considering B, it has to be a subset of U. In that case, the complement of B in A or in U is simply called the complement of B. In U, that is understood, because U is in a given discussion, U is fixed. So it is just simply called the complement of B and is denoted by, let me write it here, and is denoted by B suffix C or B prime. C of course denotes complement, and prime is also sometimes used. In fact, this is the one used more frequently than this one. This one has fallen out of use. Actually, these symbols are not without their problem. The same symbols are used in a different situation to mean something else. When we study functions, this same symbol also denotes the set of all functions with domain C and range or codomain B. Okay, these things will come later. And when we study analysis, if this is a set of points, then this can sometimes denote the set of limit points of B. But those things will come. For if nothing is said and sets are just sets without any additional structure, then this is how we denote complement of B in a universal set. Now, having said this, let us now go to the properties that difference and complements have. Okay. So properties there are many properties. The first one is, of course, A minus B is not equal to B minus A if A is not equal to B. The second, actually there is no first or second, I am just simply recalling the properties and writing them. What can I write? A minus A is empty set. Then actually many properties can be written. Shall I show all of them, or I show the more important ones? That's what I'm thinking. Okay, let me write many of them. Yeah, there is one more. To save space, let me write 3 here. More important property. If you take the complement of a set and then take its complement, you get the set back. Okay. 4. The complement of a universal set is the empty set, and the complement of the empty set is a universal set. Now you see, just a property like this may not make sense, because universal set is not something unique. So you can write this only when you have decided on a universal set. Then you can write complement. Because you see, otherwise without universal set, this complement itself does not make sense. For you to be able to think of complement, first of all there should be universal set. Because otherwise, complement of the given set in what universe are you considering? That should be made clear first of all. 5. Universal set or not like this. If A is a subset of B. Okay, if A is a subset of B, we already know what complement of A in B means. It is A minus A minus B. A minus B or B minus A? No, it's not A minus B, it's B minus A. We already know what complement of A in B means. It's B minus A, because B is the bigger one, A is the subset. So whatever is there in B that is not in A, that is the complement of A in B, B minus A. But what happens to A minus B? It is empty. Because if you see, it is the same situation like this. This is A, this is B, A is a subset of B. If we are subtracting the larger set from the smaller subset, then nothing is left. So you get empty set. Okay, so this is the 5th property. But apart from these, the more important one, it has a name. I think I have there are some more also. Yeah, I forgot about them. It's difficult to remember all the things. I mean, once you are given something, then it's easy to say something about that, but to remember all the properties unless you are always dealing with them. It's somewhat difficult to remember. A minus B can also be written as A intersection B complement. So these are some of the properties that are not obvious. These are somehow you can make sense of them just by thinking about them. These, however, have to be treated carefully. What more? Okay, this one I have already written. Have I left out some? Oh, yes. Partition. Yeah. A union A complement is universal set, and A intersection A complement is empty. Number 8. This is the most important by far. De Morgan's laws. There are two, okay. It says that if you take union of two sets and their complement, then this is equal to the intersection of their complements. And number 2, if you take the intersection of two elements and their complement, then it is the union of their complements. Okay, so these are some properties involving difference, complements, union, intersection, all those things. Okay, now we come to the proof. I will prove only one De Morgan's law. Others I leave to you as exercises. Some of them may be challenging, but think about them. Okay, eventually I will prove all of them at one point or another, but you try to prove them. So I decide to prove only this one. Only one De Morgan's law. As usual, proving means you have to show this is a subset of this and this is a subset of this. So, what I do, I take an element x in the first set. Now my intention is to prove that this is a subset of this. That means any element here will belong to this. What does this mean? It means that x is, it looks like this. You can draw the Venn diagram, so this will make the thing much clearer. This is U. As we have already said or discussed, universal set is drawn as a rectangle. This is A, this is B. So x belongs to A union B complement. That means x is here. A union B is this whole thing. A union B complement is this. That is, x belongs to U and x does not belong to A union B. X belongs to U but x does not belong to A union B. This can be written as x belongs to U and, okay, now x does not belong to A union B means x can neither be in A nor in B, because if it belongs to A or B, then it will belong to A union B, which is not the case. And x does not belong to A and x does not belong to B. Okay. Now, What does this mean? I can also write it like this. X belongs to U and X does not belong to A. Okay? And X belongs to U and X does not belong to B. I am considering X belongs to U 2 times, but I can say that no, because it's anyway true. X is in U and X is not in A. And at the same time, X is in U and X is not in B. But X being in U and not in A means X is in U minus A. Being in U and not in A means it's in this difference. But this difference is what? Complement of A, because U is universal set, so I can speak of complements. So X belongs to A complement. Similarly, from this part, X belongs to U and X does not belong to B means X belongs to B complement. But now we have AND, so this is intersection. X belongs to A complement intersection B complement. So we have proved that any element here is also here. That means we have proved that A union B complement is a subset of A complement intersection B complement. The other way around, where you consider an element here and prove that is here, you try that yourself. It's actually nothing but you start here and trace your steps back. Okay, that's what you have to do, but make sure it's not that you just go on writing like this without understanding anything and the proof is over. Not like that. You have to understand that this, once you assume this, that really implies this one, that this one really implies this one. Like that, you have to go back and you will prove that this is also a subset of this. That will give you equality, and that is one of the De Morgan's laws. Okay, now I have forgotten to tell you about one or actually two laws that involve both union and intersection. They are called distributive laws. And they look like this. A union B intersection C, they involve both union and intersection, equals A union B intersection A union C. There is one more where we interchange the union and intersections. A intersection B union C is A intersection B union A intersection C. These are called the distributive laws. These also I will not prove, and I suggest you to refer back to the distributive laws that we had in mathematical logic. This law from mathematical logic will be used in proving this one, because we have OR and we have AND. It's nothing difficult at all. You just have to take an element here and you will see that by using this properly the way we have been doing, you will see that that element is here also, proving that this is a subset of this and coming back that way. And the other one will be used in proving this one. Okay, so these are about basically about the first three operations on sets. But there is one more, and this one is by far more familiar than the last three. Why, you will understand pretty soon. Cartesian product of two sets for sets A and B their Cartesian product or I can write like this. Actually this also, like difference of two sets, this also is not commutative and depends on the order. Their Cartesian product A cross B is defined as A cross B is equal to A comma B such that A belongs to A and B belongs to B. Now this one needs more explanation. What is this A comma B? Right? What is this A comma B? You see, most of us have drawn graphs, right? In school level, we have been asked to draw graphs of some equations which look like this. For example, y is equal to x. We have been asked to draw the graph of this equation. So what we have done, we have taken a graph paper where you have all the axes, all the what can I say, all the vertical lines, all the horizontal lines, making small squares in between, and the graph paper looks like a grid. Okay, now there what we have done, we have calibrated using our scale. After choosing some unit length, we have done something like this. We marked off points like this on the x-axis as well as on the y-axis. -1, -2 and so on. We also know this is the positive side of the x-axis. All these things have come in school. Then what have we done? We have constructed a table like this, x, y, and we have put various values for x and y. For example, if I take 1, then I get 1 because x and y are equal. If I take -1, I get -1. If I take 2, I get 2, -2, -2. So after that, what we have done, we have put points on the graph paper, points on the plane of the graph paper by considering their x coordinate and y coordinate. We read of the x coordinate, what is this point? Its x coordinate is 1 and y coordinate is 1. So we do like this, 1 along by 1. So this is my point, 1 comma 1. After that, -1 comma -1. Like that, 2 comma 2. And then we have joined these with a line. This is the graph, right? Graph of this equation. Why I am telling you these things? It's because we are already familiar with points on the plane. They look like this. Okay. Now, from your prior experience with these things, is 1 comma 2 and 2 comma 1, are they equal? They are not equal. 1 comma 2 is this point and 2 comma 1 is this point. This is 1 comma 2 and this is 2 comma 1, and they are not equal. That's why these are called pairs of points or pairs of numbers, but not just any pair. Unlike this set, in sets order does not matter. 1 comma 2 is equal to 2 comma 1. It does not matter in what order or arrangement you write the elements. That's why they are called, it can be called a pair of two numbers. But this is called an ordered pair. Order matters. 1 comma 2 is different from 2 comma 1. There is a first coordinate and a second coordinate. That first and second, that matters. Okay. In sets we don't have anything like first element, second element, no. That is not there in sets. Sets don't have any order with them. You can choose some particular order to write a set down, but that does not matter. That is not a part of the set. However, for ordered pairs, order is important. Now here, this is also an ordered pair, but instead of numbers, we have elements from the two sets. Okay, and that way you get Cartesian product of two sets. I have shown this thing only to make you recall this concept of ordered pairs or points on a plane. Now this of course cannot be drawn as a graph because A and B can be any sets, but you get my idea. This is the set of all ordered pairs where the first coordinate comes from A and the second coordinate comes from B. Now if we take an example, it will be more clear. Let us take the first example that we have taken, 1 comma 2 and 2 comma 3. But now we are performing Cartesian product. By the way, Cartesian product, this name is based on the mathematician René Descartes. Okay, he introduced this Cartesian coordinate system, which is used in drawing these graphs, and some of you who are familiar with coordinate geometry, they will know about these equations and these things. It's just basically what it does, what can I say? It makes a link between algebra and geometry. Geometry is this line. This is a geometrical object. Algebra is this equation, y equal to x. It links them. Okay, so that study of geometry is transformed into a study of algebra. When you go to higher parts of mathematics, coordinate geometry will become more and more advanced, and it will be turned into something called algebraic geometry. This is by far the toughest and most interesting part of mathematics. The deepest theorems or the deepest results occur here. Okay, by saying it's the toughest, I don't mean to discourage you, but it's at this stage it is far beyond our ability to show anything at this stage, but at one point we will touch this. Okay, algebraic geometry. So I am getting way ahead of myself. So let us come back to earth and calculate this Cartesian product. Okay, according to the definition of Cartesian products, what should I write? My elements are not just ordinary elements, but ordered pairs, where the first coordinate comes from the first set and the second coordinate comes from the second set. So how many of them can we write? The first coordinate can be 1 or 2 because 2 is here. But the second coordinate can be 2 or 3. So I can write 1 comma 2 and another element will be 1 comma 3. So this one is coming from here and 2 and 3. But we can write more. The first coordinate can be 2 also. So 2 and the second coordinate is 2, 2 comma 3. So this is the Cartesian product of these two sets. Okay. So you get the point. You have to write down ordered pairs of elements where the first element is coming from the first set and the second element is coming from the second set. Now you have to write all such ordered pairs. The collection of all such ordered pairs is the Cartesian product, is the set. Okay. And you can see one more thing, that Cartesian product quickly becomes unmanageable. I mean, it becomes very large. If you try to write the Cartesian product of these two sets, then the first coordinate can be 1. When the first coordinate is 1, the second coordinate can be 1 or 2 or 3. When the first coordinate is 2, again the second coordinate can be either 1 or 2 or 3. So this is the Cartesian product of these two sets. So unlike union, intersection, those things,